Comets intrigue us by the long, extended dust tails that flow away from the comet's nucleus when it comes close to the Sun. The dust tail flows away from the comet's nucleus when the ice changes state from ice to gas due to the Sun's energy. Mindful that comets originated from the earliest times of our solar system, we would like to know how they remained intact for so many billions of years. Therefore, we would like to know how tightly bound together are the dust particles on the comet's surface. We address this question with experiments that reproduce the low pressure and low gravity conditions on the surface of a comet. Let's go for the ride together. Many studies assume that the dust is a very simple silicate material, but we now know from comet missions such as Giotto and Stardust and Rosetta, as well as studies of meteorites, that it's actually a complex mixture of minerals. And so we compare the difference in cohesiveness of these different representative dust sample materials. We find subtle but critical differences in the force that is required to break apart samples of different material. And the TEMPusVOLA experiment consists of multiple pressure vessels that allow us to study different aspects of how particles interact aerodynamically in the context of planet formation. And this allows us to go deeper in our understanding of the earliest stages of the formation of planetary systems. How is it possible that the dust that was initially diffuse in the protostellar nebula started to form structures that were the size of a comet? Theoretical predictions tell us that turbulence in protoplanetary disks generate forces that can either aggregate particles close together or cause them to be diffuse and disordered. In the middle of the last century, it was predicted that a so-called Kelvin-Helmholtz-like fluid instability would form in the disk and prevent the dust from forming dense structures. However, the fluid in this case is very special, since it is under vacuum and the dust particles themselves are one of the flowing elements. For the first time, we generated an analogous system in our experiments and demonstrated the feasibility of this mechanism to generate patterns in the flow of dust and gas. We studied the early phases in the development of this instability and demonstrated the potential for it to reach its fully developed state. For this, we need to send the experiment to space for longer-term microgravity. So from my perspective, the only direction is up.